Elementary matrices. Elementary matrices and row operations. We'll begin by taking a look at elementary matrices. And an elementary matrix is one that can be obtained from the identity matrix by a single elementary row operation. So let's remember that the identity matrix, in this case for a 3 by 3, would be 1 0 0 0 1 0 0 0 1. So essentially we're asking the question, in looking at our first practice question, could I obtain this matrix by doing just one row operation to that identity matrix? And it looks like if I were to swap or interchange rows 1 and 2, I would get back to the identity matrix. So this is an elementary matrix. Let's look at the one just beneath it. This is in the correct space, 0 0 1 for the third row. 1 0 0 would have to swap, but the problem is if I swapped, I would end up with 1 0 0 0 0 1, and in the middle 2 1 0. So I could do one row operation, but it wouldn't get me back to the identity. So this one is not a elementary matrix because it would take more than one step. Let's take a look at the next column of questions. I'm going to go ahead and put a green check mark next to this one. Looking at 1 0 0, that's where I want it to be. 0 0 1, that's where I want it to be. And it looks like the only thing wrong with this is that it's a 5. So I could take this times 1/5. That would be one row operation to get me back to the identity. So because it's one row operation, it is an elementary matrix. Just down from that, we can see without doing anything that this is not an elementary matrix, and that's because it has to be a square matrix n by n. So this is obviously missing a row and therefore not an elementary matrix. Let's look at the third column of questions. We have 1 0 0 0 0 1, and in the middle, this one's a little bit different. I have 0, 1, and 3. Now the good news is I have all of the ones in the correct spot, and all I would have to do is take -3 times row 3 and add it to row 2. So that's just one row operation as well. So this is an elementary matrix. Whereas our final example, notice we have a row of zeros. We'll never be able to get back to 0 0 1 with all zeros in that column. So this is not an elementary matrix. What do elementary matrices do for us? Well, we can actually use elementary matrices to perform any of the 3 elementary row operations. So instead of showing interchange or scaling or replacement, we can use an elementary matrix to do that or to perform that row operation. So for instance, if I wanted to interchange rows 1 and rows 2 in this matrix A, I can multiply that by an elementary matrix. And that elementary matrix, if you'll notice, has rows 1 and 2 swapped from the original identity matrix. And what I want it to do is swap rows 1 and row 2 in matrix A. So let's do this one by hand so we can see what's going to happen. I'm going to take 0 1 0 and write it as a column. That gives me 0 plus 1 plus 0, which is 1. 0 plus 1 plus 0, which is 1. And 0 plus 2 plus 0, which is 2. And then I'm going to move on to the next row. 1 0 0. 0 plus 0 plus 0, which is 0. 4 plus 0 plus 0, which is 4. And 3 plus 0 plus 0, which is 3. And then for our last row, turned column, 0 0 1, we get 0 plus 0 plus 5, 0 plus 0 plus 0, 0 plus 0 plus 1. So what has happened from multiplying those two, exactly what we wanted to happen. Row 1 and row 2 are swapped, and all we had to do was multiply by that elementary matrix. So let's get rid of my work there. Now, we're not going to multiply the others out by hand just for time's sake, but feel free to do that on your own. Let's say I have, this is matrix A, and you can see matrix A has some fractions. So what if I wanted to multiply by 5 in R2? Then I'm replacing the 1 in R2 by 5 to indicate that I'm multiplying or scaling by 5. And again, what would happen? Only row 2 would be affected, and it would be multiplied by 5. And replacement, remember that's the one we used most often. Again, if this is matrix A, I can do replacement. Now this one's the trickiest, but this one's saying -2 row 1 plus row 2 is my new row 2. So notice I have a -2 in the first column to indicate that I'm using row 1, and then row 2, and then my new row 2, meaning that it's happening in row 2. And again, feel free to do the matrix the long way to make sure that you're doing it correctly. But notice I do get -2 times row 1 plus row 2 is my new row 2. So I get it just like I wanted it using an elementary matrix rather than row operations. Now for the remainder of this video, I'm going to continue showing both row operations and the elementary matrices. Your textbook doesn't show a lot of the row operations after that initial introduction to this is how they compare, but I just kept them in there the whole time just so you could see exactly how to write the elementary matrix using the row operation. So for this question, we're going to find a sequence of elementary matrices that can be used to write the matrix A in row echelon form. So we have matrix A, and we want to write it in row echelon form. So again, how do we do that? Well, we're just going to start using our row operations. So if I were doing this using row operations, my initial step would be to try to get rid of that 1, which is what I've done. And now I'm just writing what elementary row operation did I use? Well, I swapped these two rows, row 1 and row 2 swapped. So again, my elementary row operation has those two rows swapped. Next, again, I already have the 1 where I want it and the 0 where I want it, and now I would want to take care of that 2. So let's take -2 times row 1 plus row 3 is my new row 3. What would that look like as an elementary matrix? Again, -2 in the first column plus 1R3, and that's written in the third row. And we're almost where we want to be. We've got a 1, we've got a 1, we have a 2 here, so instead of a 2, I want that to be a 1, so I'm going to multiply everything by 1/2. So I'm taking 1/2 of row 3 is my new row 3, and then again, that is the elementary matrix where I've replaced 1 with 1/2 in the third row. Now, I'm going to finish that question. Use the sequence of elementary matrices to write the matrix A in row echelon form. To write A in row echelon form, I'm going to take E3 times E2 times E1 times A. So this was my first elementary matrix, my second, my third. Notice I'm writing them in the opposite order, 3, 2, 1 times A. And then I'm going to simply multiply. So I'm going to start multiplying here, and then here, and then here, and that is B. So I've now written this in row echelon form using those elementary matrices. Let's take a look at a couple of theorems and definitions. So one is a definition, row equivalence. We know that two matrices are row equivalent when there exists a finite number of elementary matrices such that B is equal to EK times EK minus 1 all the way down to E1. So taking this back to what we just did, we said write A in row echelon form. We're saying that A is row equivalent to B. So A was not in row echelon form, but once we took it times E3, E2, E1 times A, we were able to write it as B. So because I could multiply by elementary matrices, I could say that A and B are row equivalent. Theorem, elementary matrices are invertible. So if E is an elementary matrix, then E inverse exists and is an elementary matrix. We're going to use this on our next question, because we're going to follow the same steps to find the elementary matrices, but then we're going to use the inverse to find our solution instead. And property of invertible matrices says a square matrix A is invertible if and only if it can be written as the product of elementary matrices. We're now going to take a look at using the inverse of an elementary matrix. So in our past example, we took E3 times E2 times E1 times A to equal some other matrix. In this case, we're going to kind of go in reverse, because we want what sequence will give us A as the solution. So we want A is equal to what? Now this is why these inverses will come into play. We're going to be using the inverse of those elementary matrices. And the reason for that is if A is on this side, if A is the output, then I'm going to have to do some getting rid of things, right? I'm going to have to get rid of E3 using the inverse of E3. And then I would have to get rid of E2 using the inverse of E2, and get rid of E1 using the inverse of E1, and that would leave me with A. So let's take a look at the process. The first part of the process we're very used to. We've got our original matrix, we've got our row operation, we've got our resultant matrix, and then we have the elementary matrix that we used. As I said before, if you want to skip this, that's fine, as long as you understand where E1 is coming from. In this case, we're saying -3 row 1 plus row 2. This indicates it's -3 row 1 being added to row 2 because it's in row 2. And then I'll continue. I need this to be a 1, so I'm going to take 1/2 of row 2. And as an elementary matrix, that looks like 1, 0, 0, 1/2. And then I need the 2 to be a 0, so that looks like -2 row 2 plus row 1 to be my new row 1. And I end up at reduced row echelon form, which is what I wanted. So my last elementary matrix is 1, -2, 0, 1. Now I want to find the inverse of each of those matrices. So the inverse of each of those matrices is just the same inverse we're used to. So to find the inverse, I would take 1 times 1 minus -3 times 0, so that's 1 divided by 1. I would change the location of 1 and 1 and change the sign of 0 and -3, and we can see that's where this inverse matrix came from. I encourage you at this point to use a matrix calculator is just fine. It's pretty straightforward on a 2 by 2 matrix. I could see that the opposite of multiplying by -3 would be multiplying by +3, but it's not going to be as straightforward on a 3 by 3 matrix. So again, find the inverse of each of those matrices, and then in order to find the outcome of A, as I said, we're going to be taking the inverse of E1, E2, E3 in this case. And just for fun, I went ahead and multiplied it out. So this is the sequence. So this is the solution to my question. Find the sequence of elementary matrices whose product is the non-singular matrix A. But this part is basically showing my work. I went ahead and multiplied these two, and then multiplied by that last matrix, and found that I did, in fact, end up at A. I often get feedback from my students about how there are so many things in linear algebra that are the same. So this is exactly why we have slides like this in videos, because all of these statements, these 5 statements, all essentially mean the same thing. So if we have A that's an n by n matrix, which means it's a square matrix, then the statements below are equivalent. A is invertible. Now keep in mind, I'm not saying all square matrices are invertible. I'm saying that A is invertible is the same as me saying I can write A as a product of elementary matrices. Or the same as me saying that AX equals B has a unique solution for every column matrix B. So again, we're saying if we have A and then we have X, which is a column vector, equal to B, which is a column vector, there's going to be a solution in X for B1, there's going to be a solution in X for B2, for B3, and so forth. So there is going to be a solution for every column matrix B. AX equals 0, remember that's the 0 vector, has only the trivial solution being all zeros, and that A is row equivalent to I sub n. Again, this means the identity 1 0 0 0 1 0 0 0 1 for a 3 by 3 matrix. And again, these are all saying the same thing. We're saying A is invertible. It has a solution for any column matrix B. It has the trivial solution for the 0 matrix. It has row equivalent to the identity and can be written as the product of elementary matrices. The LU factorization. What we want to do is to rewrite a matrix A as the product of two other matrices. That's called the LU factorization. L represents a lower triangular matrix and U represents an upper triangular matrix. So before we talk about the LU factorization, let's make sure we understand a lower and upper triangular matrix. We know if we have a matrix that is a square matrix, so it's n by n, and we have whatever occurs along the diagonal. If you have everything above that diagonal is zeros, that's considered a lower triangular matrix. Lower because all of the coefficients occur below or on the lower triangular side. If you have all of the zeros here below, that's considered an upper triangular matrix because again, all of the coefficients occur above that. So what we're trying to do is we're trying to take a matrix A and rewrite it as the product of two matrices, one that is a lower triangular matrix and one that is an upper. Now, you'll notice a lot of the same steps that we have been doing using those elementary matrices. So for instance, and again, I'm choosing a very easy example for this first one because it's a 2 by 2 and it only required one step. We will do a more complicated example in a moment. But my first step would be to rewrite the matrix A, so this was matrix A, and say, what would be my first step in Gaussian elimination? Well, I would make sure this bottom value is 0. And guess what? Now, this is an upper triangular matrix. Again, because we have whatever's happening along the diagonal, and everything below that diagonal is zeros. So this is U in my lower upper. Now what do I have to do here? I have to think, I don't want to deal with row operations anymore. I want to deal with elementary matrices. So this is the matrix that I used, and I want to use the inverse of that. Now why do I want to use the inverse of that? Because in order to find U, I took E1 times A, right? Because we know that the E came first, and that would give us my result, which is U, which means that A is equal to the inverse multiplied on the left-hand side. So A is equal to the inverse of E1 U. So in this case, it was very, very easy because I only had one to deal with. But notice this is L, and U was from my reduced matrix. The reason that you might want to use LU factorization is to solve a system. So I'm going to put together our example of solving a system with writing the LU factorization of a 3 by 3 matrix. So the first several steps will be finding the LU factorization, and then we'll use that to go ahead and solve the system. So the first thing we should do here in solving a system is to write the coefficient matrix. So for right now, I'm not concerned about the 1, 2, or -2. I'm concerned about 2, 1, 0, 0, 1, -1, -2, 1, 1, which is exactly what I have here. So that's step 1, write the coefficient matrix. Step 2 is going to take our coefficient matrix and we're going to rewrite it using row operations in upper triangular form. So again, we're going to keep track of the matrices that we use. Whether or not you choose to show this row operation is on you. It's completely up to you if you choose to do that. If you're just learning elementary matrices, it might be helpful. Row 1 plus row 3 is my new row 3. How does that translate into an elementary matrix? I would have a 1 here to indicate that I'm adding row 1 to row 3. Next, we can see it's not quite in upper triangular form yet because of this 2, so that's what I have to do next. I'm going to take -2 times row 2, add it to row 3 to get my new row 3. That now gives me upper triangular form. This is U. What's the last elementary matrix that I used? I took -2 times row 2 to add to row 3 to get my new row 3. So there are the two elementary matrices and my value for U. Step 3, I'm going to find L by multiplying by the inverses of the elementary matrices used in step 2. So I've recopied those matrices here, but again, I encourage you to use a matrix calculator to find those inverses. So the inverse of E1 and the inverse of E2, I just used a matrix calculator to find those. If you want to do the work the long way, feel free. There's just already a lot of steps involved, so using a calculator for this portion is just fine. From here, I'm going to write the LU factorization. So A is equal to the inverse of E1 and of E2, and then times U. So remember, this product is going to be L. So I'm going to go ahead and multiply in that order, E1 inverse, E2 inverse, to get L. So now this is L, and this is U, the same U that I had in that first step. So this is the LU factorization. Now, if they said, find the LU factorization, this would be the end. This would be where I would stop. So from this point forward, this is new information for now that we know the LU factorization, how can we use it to solve the system? The next step to solve our system using LU factorization is to solve the system Ly is equal to B. And let's talk about where those values came from. So this is L, this is our lower triangular matrix that we did before. We just found that on our last step. Y is simply a column matrix full of Y variables with subscript matching how many we have. And B comes from our original solutions just like before. Remember, we always have AX equals B, where B is those solutions. So that's what we're dealing with here. Now, what am I trying to do? I'm trying to solve for Y. So I want to find what does Y1 equal, what does Y2 equal, what does Y3 equal. Now, the good news is I can use something called front substitution. So in back substitution, that's where we have the zeros here, right? And we can say, well, this last one is equal to -2 and so forth. Well, in this case, because it's a lower triangular matrix, I'm going to say Y1 is equal to 1 without doing any work. And then Y2 is equal to 2 without doing any work. And Y3 is equal to -1 Y1 and 2 Y2 and 1 Y3, and that's equal to -2. Replace those values of 1 and 2 and solve for Y3, which is -5. So now I have my solutions for Y, and I'm going to again think about them as a column matrix. That brings us to the last step, which is to solve the system U. This is the same U we found previously. X, that's our X's we're trying to solve for, where X is the solution to the system, is equal to y. This is what we just found on step 4, 1, 2, negative 5. To solve this one, I'm going to use back substitution, which is what I'm used to, because again, I've got all the zeros down here, so it's an upper triangular matrix. So 3x3 is equal to negative 5. And I'm just going to solve that to get negative 5/3. And then I have x2 minus x3 is equal to 2. Replace x3 with 5/3, so minus negative made it plus. Subtract 5/3 from each side to get x2 is equal to 1/3. And then again, 2x1 plus x2 plus 0x3 is equal to 1. And replace x2 with 1/3. Subtract 1/3 from each side, divide by 2, and I get x1 is equal to 1/3. So my solution to the original system is 1/3, 1/3, negative 5/3. Coming up next is section 2.5, Markov chains.